calculus students! So in this video we are going to be learning about the fundamental theorem of calculus part 2. But before we learn about that, we're going to do a little investigation with example 8. So example 8 is asking us to do a few things. So it says given this f, big F, which is the integral from 3 to x of 2t plus 1 dt, find a simplified expanded version of f of x. So that's where we're going to start off right here. I'm going to try to color code. So this is what we're doing first, by evaluating the definite integral. So we're going to expand this by solving that definite integral. Okay, so applying the definite integral means finding the antiderivative and evaluating from 3 to x. So this is going to be 1/3 t cubed plus 1/2 t squared plus t, and we're evaluating from 3 to x. Okay. And we're going to continue to expand by plugging in the values. So we're going to get x cubed over 3 plus x squared over 2 plus x minus, plugging in 3, get 27 over 3 plus 9/2 plus 3. Now we can combine like terms to simplify. None of these things have common terms, so they will just all stay separate. But we can combine these things in the parentheses. So this goes to 9, this reduces to 4.5. So in the parentheses we have 16.5, so it's minus 16.5. Alright, so we did that first step. I'm going to switch colors to do this next one. So once you find f, find its derivative, f prime. So we're going to find the derivative f prime. If I bring down the 3's cancel, and then I subtract 1 from my exponent for the derivative. Same thing here, bring down the 2's cancel, and then my new exponent is just x to the first power. This becomes 1, and then the derivative of negative 16.5 is 0. So there's my derivative. And then I'm going to do this last part. What do we notice? And so looking at the final answer that I got, I do notice a likeness, if that's the word, between my final solution and the solution that I started with, or the equation that I started with. So right here, it's very similar to right here. I just noticed that my final equation is in terms of x. So I'm going to kind of make a little comment about this, is that it's the same function. I started with, but it's in terms of x. Okay, so that's one thing. And so what I think might have happened is that I took the integral, and then I took the derivative. So what I think happened is the integral and the derivative kind of canceled each other out because they're inverses of each other, which we learned in the previous video. So one thing that I'm also noticing is that this term here, because it came from the term with a constant 3, it just canceled out. So when we plug in 3, we just get a regular constant. In this case, we got negative 16.5, and the derivative of the constant term cancels out. Okay. Whereas this x term replaces the t value. And so this little exploration leads us directly into the fundamental theorem of calculus part 2, which I use this, it's just slightly different. I'm just going to call it FTC part 2, which is slightly different from what the person who made the notes called it. So what the fundamental theorem of calculus part 2 says is that if we have a function, big F, and if this big F consists of an integral of little f, then what we know is that big F prime equals f, or more formally, the derivative of the integral will end up just being the regular function. So these two things are saying the same thing. You're more likely to see it in this more formal notation written below. Okay, so the application of this, I think you're going to end up liking. I'm going to switch back to my purple. So here I have the derivative of the integral. So the derivative of the integral, because they are inverses of each other, they cancel each other out. But since I am evaluating this in terms of x, my variable will become x instead of t. There it is, using FTC Part 2. Same thing over here. I have my derivative, and I have my integral, and I am evaluating it in terms of x. And since this is just a constant, that term, whatever I get there, will cancel out. And so I end up getting the square root of x cubed times sine of x. And that's it. So I want you to try part C on your own. Pause me and try part C on your own. Okay, and so now you have an answer. You can check with mine. Again, the derivative and the integral, because they are inverses, they cancel each other out. My new variable is x, so I get e to the x times square root of x plus x squared divided by ln of x. Did you get it? Yay, nice job! Alright, so far I hope that you're thinking that FTC Part 2 is super duper easy. We've already covered like the main idea that derivatives and integrals are inverses of each other. But we do have to add one slight more challenge. And this arises when we have special cases where we have functions as the upper and lower bounds. So in the previous problems that we did, it always looked something like this, where it was just some constant to x of f of t dt. Okay, and so we would talk about, oh, since this is a constant, we just get a number and this goes away. And then the x becomes the new variable. So that is what it looked like in all the other problems that we did. So going back to the previous page, we always had just a constant to x, and so x became the new variable. The problems that we're going to look here might have a variable, a different function, a more complicated function as the upper and lower bound. And so what is going to happen here is that we have to do the chain rule. Okay, and I know you love the chain rule. So I'm going to kind of just exhibit how we would use the chain rule in the easier problems so that hopefully it makes more sense with these more challenging ones. So secretly, I was using the chain rule in part A. I just didn't really show you what was happening. So we'll do this in red. What I was secretly doing, if I kind of expand this out, so I was taking the derivative of this function here. And so basically I was taking the derivative and I'm gonna apply the fundamental theorem of calculus part 1. So whatever I get here, big F of t, I'm evaluating from 1 to x. And then I would expand this out just like we did in example 8, and I get big F of x minus big F of 1, right? And now I would apply the derivative. So taking the derivative of big F of x, I get little f of x. But then I do have to use the chain rule. So little f of x, the derivative of x is just 1, right? And then the derivative of big F of 1 would be little f of 1 times the derivative on the inside. The derivative of 1 is 0. So this term cancels out, just like I've been talking about. So the term with just the constant cancels out, and here's why. Because of the chain rule. The derivative of a constant is just 0. So f of x times 1 means I just go back to my original function, and instead of t, I use x, secant of x. So this is kind of like the long way of doing the fundamental theorem of calculus part 2, just like we did in example 8. Secretly, we've been using the chain rule the whole time. So I hope it's not too confusing when we go to these other problems and do that as well. Okay, so let's give them a try. All right, so we're evaluating this from 1 to 2x cubed. So I'll kind of show you the long process and then the short process. So the long process is if I had to expand this out. So I'm taking the derivative. I'll just call it big F of t, if this is my little f of t. And I'm evaluating the derivative from 1 to 2x cubed. And so expanding this out, I'm taking the derivative of big F of 2x cubed minus big F of 1. And so I've applied the fundamental theorem of calculus part 1, and now I'll take the derivative. So the derivative of big F is little f of 2x cubed. The inside stays the same, but then I have to multiply times the derivative on the inside using chain rule. So the derivative on the inside is 6x squared. And then I'll take the derivative of the second part. The derivative on the outside is f, inside stays the same, times the derivative on the inside. So this constant term, same as before, cancels out, and I'm just left with 6x squared times f of 2x cubed. Here's my f function, so that's what I'm going to plug it into. So it's secant squared of 2x cubed times 6x squared. Okay, so that is the long way to do it. The short way to do it is just to use the most general form of our fundamental theorem of calculus part 2. So using our outer function right there, plugging in, I already kind of highlighted them in red, so I'll just put this right here, plugging in the bounds, so the upper and lower bound, and then multiplying using the chain rule, so the derivative of those bounds. Okay, so we are going to use, we're going to use the short version right here in part B. So instead of doing it the long way, I'm just going to apply this definition that I'll keep in the screen right there. Okay, so my f, here's my f, and I will highlight in red my bounds that I've got to plug in, and then in yellow I'll do my chain rule. Okay, so I've got to plug in 7. So it's 7 squared plus 5 times 7 times the derivative of 7, which is 0, minus, now I'm plugging in e to the x, so e to the x squared plus 5 e to the x. And then I have to multiply times the derivative. The derivative of e to the x is just e to the x. So there's my chain rule. So in red, I'll put where my bounds are. So that's when I plugged in the 7s and the e to the x. And I plugged those into my f. And then in yellow, I will highlight where I did the chain rule, right there. Okay, so what this looks like is, I can distribute this. I'm just going to simplify. So I have my 0 term, that goes to 0. E to the x squared times e to the x. I would add the two exponents together, and I'll get e to the 3x plus 5e to the 2x. Gotta make sure to use my parentheses because that negative sign is out there. So this is negative e to the 3x minus 5e to the 2x. Cool. We'll show this one last time with this kind of more challenging one. If you are feeling good about this, I highly encourage you just to try it on your own and then fast forward and check with my answer. But if you are feeling confused, go ahead and watch the full thing. But if you feel good, you feel good. Okay, so here is my f of t. In red, I'll put my bounds. And then when I get to it in yellow, I'll show where the chain rule is. Okay. So first I'm going to plug in the b value, the upper bound. So this is ln of 3 to the x. And then times the derivative on the inside. The derivative of 3 to the x is 3 to the x times ln of 3. And then minus. I always want to be careful. I'm going to use like brackets to make sure I get everything in there. So now ln, and I'll plug in my lower bound, so 2 plus sine of 2x. And then chain rule times the derivative on the inside is going to be cosine of 2x times 2. So I kind of had to do a double chain rule right there, since I had a function inside of my function. Great. So just so you can be sure where everything came from, here are my inputs from the bounds, and then the effects of the chain rule are right here. There's the chain rule, and there's the chain rule. Cool. I'm just going to leave it like that. It's a long mess, but that's okay. So that is it for the Fundamental Theorem of Calculus Part 2. Obviously, it gets a little bit more complicated when we have functions as our upper and lower bounds, but it can also just be as simple as the fact that the integral and the derivative are inverses of each other.